Previously, we've discussed advanced geodatabase objects including feature datasets, relationship classes, feature subtypes, attribute domains, and contingent values. Today, we'll talk about utility networks, transportation networks, network topology, and metadata, all advanced objects that can be stored in a geodatabase. There are three primary types of networks that we can store in a geodatabase: utility networks, transportation networks, and topological networks. Utility networks are directed networks in which the network directs the agent in traversing the network. In this case, water, for example, traversing a stream network. Transportation networks are undirected networks in which the agent independently traverses the network. For example, how a car can traverse a street network by deciding which route it wants to take. Topological networks are a set of rules that define behavior between integrated features. And we can break topological networks into two types: geodatabase topology and map topology. Geodatabase topology is a persistent topology that is stored as an object in a geodatabase. It persists in the geodatabase. Map topology is a temporary topology cached for a single ArcGIS session. So map topology only exists for the length of an ArcGIS edit session, while geodatabase topology is an object that's created in a geodatabase and persists as long as you have it in the geodatabase. To create a network in ArcGIS, it has to be created in an ESRI geodatabase feature dataset. So feature datasets are geodatabase folders that thematically organize your data and also enforce coordinate systems. And it's that second aspect, enforcing coordinate systems, is why we use feature datasets to store our networks, because we want all of the feature classes that participate in the network to be in the same coordinate system. If you look at the example on the right of the catalog pane and the Sunset Valley feature dataset, when you want to create a new topological network, you can just right-click in the catalog pane on a feature dataset and select New, and then choose the type of network, whether it be a geodatabase topological network or a transportation network dataset or a more specialized network dataset like a parcel fabric. Now, if you look in the feature dataset itself, you can see that there is a parcels geodatabase topology present and a streets transportation network, but there's also a streams trace network. While geodatabase topology is a rule-based network and a network dataset is a directed network, a trace network is a undirected network. So the network directs the agent as it traverses the network. In this case, it's with the water that's flowing through the streams. A more specialized trace network that we don't see listed here is a utility network that allows you to model how electricity or water flows through a utility network. Now, as previously stated, a feature dataset can contain multiple networks, but feature classes can only participate in one network at a time. And if you look at the Sunset Valley feature dataset, I can see multiple networks: the parcels geodatabase topology, the streams trace network, and the streets transportation network. But for example, in the streams trace network, the participating feature class is the line streams underscore COA feature class. Because that particular feature class is participating in the streams trace network, it cannot additionally participate in the parcels geodatabase topology or the streets transportation network at the same time. Now, utility networks model connectivity within and between custom feature classes. They model the simple relationships that are present in a hydrological or utility network. Again, these are a directed network, so the network directs how the agent is routed. The agent always takes the same route. So when I'm in my house and I flush my potty, that is a wastewater utility network. And when I flush the potty, it always goes the exact same route through the pipes to the wastewater treatment plant. And so we use directed networks typically to model stream, water, wastewater, gas, and electrical networks. And when you update the feature classes that are participating in the utility network, you also update the underlying network at the same time. So connectivity is incrementally updated with every edit. On the right-hand side, you can see an illustration of a utility network in a neighborhood. And so the green lines or edges are transmission lines, and we'll say for power in this case. And then They are connected to each other by junctions and then connected to the neighborhood system by junctions as well. And then notice the neighborhood system distributes whatever the agent is, in this case electricity, to the houses that end in a little yellow junction. And that little yellow junction actually connects to the household system. In addition to the edges and junctions that create a utility network, we also can use attributes to model behavior imposed on the agent traversing the network. The attribute types that you can store in a utility network include weights, restrictions, and flow direction. Weights are basically how easy or hard it is for the agent to traverse an edge, for example. Restrictions can either allow or not allow the agent to traverse the edge, and flow direction can set which direction the agent flows on that edge. The flow direction is set after the network is built for utility networks, and it can be set in one of two ways. One is with the digitized edge direction. So when you first created the features that are participating in the utility network as edges, when you created a line with a from node and a to node, or a beginning node and an end node, that is the digitized edge direction, and that will set flow in your utility network. Or you can designate a source and a sink, and then utilize that to calculate flow across your network. So a source is where things begin and a sink is where they end. And so you would designate a source on one side of your network and a sink on the other side, and then it would set flow based on the location of your source and sink. Now, to create a utility network in ArcGIS, you must first prepare the feature dataset and sources. So you need to set your coordinate system and then make sure the feature classes that you want to participate in that network are stored in the same feature dataset and are not participating in any other network. Then you need to prepare your attributes, which include things like weights or restrictions, whether the line is enabled or disabled, for example. And then you create and build the network dataset. Last, you have to remember to establish the flow direction, because you can't perform any analysis on a utility network until the flow direction is established. Once you've established flow direction, you can analyze your utility network. And these are the common types of analysis that we perform on a utility network. Those are tracing analyses and connectivity analyses. And the most common form of tracing are the trace downstream and trace upstream. And if you look at the example on the right, you can see that's a trace downstream. It's a hydrological network for a single watershed. And I've created a network object that is the source, and then utilize trace downstream to trace down the network to the sink, which would be to a confluence with another major system or maybe even a major body of water. If I ran trace upstream on this same network, I would put the network object at the very bottom and do a trace upstream. And that, in this case, would highlight the entire network within this watershed, because all of the hydrological streams are upstream of the sink at the very bottom of that image. We typically use connectivity analysis to make sure that our network doesn't have any loops in it or there are any edges that are disconnected. Transportation networks model connectivity within and between transportation feature classes. So transportation networks are much more complex than utility networks because the agent can choose its path through the network. This makes it an undirected network in which the agent can choose their route. A vehicle, for example, can go right, left, straight, or make a U-turn at a four-way intersection. We typically use transportation networks to model vehicular street networks, but also other types of transportation networks as well. For example, a bus network, a train network, or maybe even a pedestrian network. And so when we combine these networks together, we call them a multimodal network, in which there are multiple modes of transportation on which an agent can take across the network. The connectivity for transportation networks is updated on demand. What that means is if you edit the underlying feature classes, for example, a street center line, then you have to go and build the transportation network again so it reflects any changes to the street center lines. So it's updated on demand. The illustration on the right shows a multimodal transportation system in which I've modeled street, bus, and rail transportation networks. And each of those networks include edges and junctions that allow you to transfer, for example, from one edge to another. And in this case, the junctions don't line up, but if they did, for example, if the rail station lined up with a bus junction, then you could transfer from the rail to the bus line. Transportation network attributes model behavior imposed on an agent traversing a network. And the types of attributes that we can model include cost, for example, how long it takes to travel along an edge, the number of lanes or the speed limit, for example, whether there are any restrictions on the route. If you have restrictions, you could route a vehicle that has hazardous cargo to use only the hazardous material routes, for example, or hierarchy. Hierarchy allows you to impose a hierarchy on your system. For example, where traveling highways might be valued over traveling roads. So even if it's the same amount of time to go the highway or the roads, you can set a hierarchy where you'd always pick the highway. An important network attribute are the turns, and the turns can be modeled as global or individual turns. Global turns are where every intersection is treated as a junction where you can traverse from one edge to the other. And so if it's a four-way intersection, you can go right, left, U-turn, or straight. Optionally, you can also model your turns, and that would allow you to restrict certain turns so that you can only, for example, take a right turn, or in the example below, if you're traveling from north to south, you can go left, straight, or U-turn, but you can't go right. To create a transportation network in ArcGIS, first you need to prepare the feature data set and sources. Again, set the coordinate system and make sure that your feature classes are stored all in the same feature data set that are going to participate in your transportation network. You also need to ensure that none of your feature classes are participating in any other network. Then you prepare your edge, junction, and turn attributes. We've talked about that already, things like the length or the speed or whether it's one-way or two-way street. And then you create and build the network data set. Once you've built your transportation network, you can use it for analyses. And there's a number of analyses that you can do, including finding the best route, the closest facility, finding service areas, creating an origin destination cost matrix, solving a vehicle routing problem, and identifying the most efficient location. And I'll give you illustrations of each of those in just a second. The three steps we utilize to analyze a transportation network are first to create a networking problem/analysis layer and set the properties for it. Then you add the network locations to be used as inputs. And last, you solve and display the results. So for example, finding the best route, you would create a routing problem or analysis layer and set any properties. Maybe, for example, you're restricting it to only hazardous material routes. Then you would add the network locations, for example, your beginning location and your ending location, and then you would solve and display the results. Here you can see illustrations of the analysis where you find the best route or find the closest facility. On the left-hand side, you can see finding the best route where you establish network locations, for example, where you are and where you want to go, and then you solve for the shortest or quickest route. When you find the closest facility, you typically have an incident that you identify as a network location, and then the facilities that are closest to that incident. And so in this example right here, I have a health emergency that is identified as an incident, and you could have one incident or you could have 1,000 incidents and run them all at the same time and see which incident is closest, for example, to the nearest hospital. A service area analysis is a really intuitive and sophisticated analysis that allows you to establish a location on a network and then identify all area that is within a certain time from that location. And it can be drive time and it could be walk time. In this example right here, we have a red location identified, and then we've solved to find the 5, 10, and 15-minute service areas from that location. Now, an origin destination cost matrix, or OD cost matrix, allows us to see the time it takes to traverse a network from each location to each other location that is on your map. So in this example right here, I have a bunch of different cities, including, for example, Buffalo, Detroit, Milwaukee, Chicago, Indianapolis, and then I've used a transportation network to calculate the transportation time between each of the destinations. Now, in the illustration right there, the graphic that gets returned, in addition to the attributes in the table, is actually what we call a spider map or a straight line map that shows a straight line connection between the origin and destination. But the time that is represented in the attribute is actually the shortest route along the transportation network. So in this example right here, Milwaukee to Detroit are the destinations, and it takes 355 minutes to travel from Milwaukee to Detroit along the transportation network. We can also use transportation networks to solve complex vehicle routing problems. We see this used for logistical companies like the US Postal Service or FedEx or Sears even, in which they'll have multiple vans or vehicles that have packages that need to be delivered, and then they'll identify all the addresses each day where they need to be delivered. And then you can use a vehicle routing problem to solve which vans or trucks get assigned which addresses and what is the most efficient route to navigate those addresses. So in this example right here, I've got 3 different vehicles, and it looks like I have, somewhere like 20 or 30 incidents or addresses that they need to go to. And I use the vehicle routing problem and the underlying transportation network to find the most efficient solution. The last type of a transportation analysis we're going to talk about is to identify the most efficient location. And with this type of analysis, your network locations include incidents and also facilities. And so basically what you're doing is for all of the incidents, you're identifying the time it takes to get to the closest facility. And we can utilize an analysis like this, for example, to look at incidences for fire stations and look how efficient our network is, and then see if we reconfigured our network by taking some fire stations offline and putting other fire stations online, what the network might look like. Or we can utilize it to add a new fire station and see how much time that will take off the incident response for all the other fire stations. Now, building a transportation network can be a little overwhelming because they can be very, very sophisticated, but we typically don't start with the most sophisticated transportation networks. Typically, we start, for example, with a street centerline file that we use to make maps. And then we might add street names so that we can attribute and label our street centerlines. And then we might add addresses, which allow us to create a geocodable street centerline file. The next step would be to add connectivity and global network attributes that allow us to route across a transportation network. And then we can create more detailed network attributes so we have a more descriptive model, or even add additional modes of transportation to create a very sophisticated transportation network. So it's much cheaper just to create a cartographic street centerline file, but it doesn't have as much function. It is much more expensive to create a multimodal network, but it has a lot more function associated with it. So it just depends on what your purpose is, and what you're trying to accomplish is going to drive what type of transportation network model you build.